Good afternoon, everyone. Thanks for coming. This is Yuchen, CTO of Cognality. And I have my co-speakers today, Jodie Su from AMD, Senior Manager of Engineering, and also Zhiming Shen, CTO of Exostellar. It really takes a village to optimize LLM serving stacks. Each of us represent a different layer of the stack. So the model application layer, the hardware acceleration layer, and the infrastructure orchestration layer. We hope this cross-layer close collaboration model in the open ecosystem continues to drive the full stack optimization from hardware to software. So as we all know, AI workloads are extremely heterogeneous, from small and mighty models to really large ones with meaningful trade-off. And this slide is just a one-dimensional view with the model size. Even for the same size model, different request shapes like token distribution, prompt structure, coming in batches can create this really bursty, unpredictable traffic burst and resource bottlenecks. For example, you may have RAG that has super long input, including both the prompt and retrieve docs, but short output. On the other hand, you may also have reasoning agents with short immediate input, but super long output. And on top of everything, you may have mission-critical production models running and the lower priority experiments causing resource contentions. Now, with agentic workflow, it becomes a Kanban system with more challenges for dysregulated serving and also the composable automation. So let's have a quick refresher. When we talk about agentic workflows, it typically falls into two patterns. On the left, humans are in control, defining deterministic code path and chaining different tools and models. On the right, LLMs are in control, dynamically planning, reasoning, and calling tools autonomously. So most production systems actually use more reliable workflow patterns on the left. In fact, most of the business problems can be solved by simple prompt chaining and structured output. So for this demo, we're going to use a really kind of a simplest, most commonly used prompt chaining, which is also the building block for the right-side system. Now, the problem we're trying to focus today is actually one simple question. How do we free up more GPU resources so we can pack more workloads, such as co-locating tightly coupled agents on the same AMD GPU? We solve this problem by fine-grained fractionalization at the gigabyte level granularity, and also combined with Q, start with a K, powerful quota and priority and preemption systems. With this context, I'll turn it to my colleague Jodie Su for a deep dive of the problem and solution design.
Thank you, Yuchen. So I'd like to cover to achieve the effectiveness of scheduling these agentic workflows on AMD GPUs. What are the common challenges and solutions? The first challenge is that GPUs are expensive. What this means is that you often have limited of them and often in short supply. So if you have to allocate them statically, say organization A have 400 GPUs, organization B have 200 GPUs, to make sure that each organization feels fair, this static allocation actually leads to high GPU waste. As we are Kubernetes, so the solution that one common solution we come up with is, why don't we pull all these GPUs into a shared cluster and then consolidate different kind of AI workloads on them and leverage what Kubernetes does the best, scheduling and binpacking different kind of AI workloads, such that it allows us to drive up the GPU utilizations. Now that we consolidate all the workloads onto the same shared cluster, we face the next question. These different AI workloads have competing priorities. For example, the agentic workflows Yuchen illustrated, they have a user waiting for it. So there's a latency requirement, such that I want to make sure the workflows finish in what the user can wait. And the other type of AI workloads like GPU batch processing or training, they don't have a latency requirement, but they do want to get as much GPU as possible. So with this in mind, then and the other thing is like, since we consolidate all organizations' GPU together, each org might want to make sure that they get some kind of fair share out of this shared cluster. So our proposed solution is to use Kueue. So Kueue is really good at giving priority scheduling such that we can make sure the latency-sensitive agentic workflows can get the GPUs in time to satisfy the user request. And we can also use the nominal quota to kind of give each organization some kind of minimum quota guarantee, and then how much they can borrow, so that people feel like, okay, I'm getting some fair share out of this shared pool. Finally, as these agentic workflow or like some kind of online inferencing a user-generated request, they could be a very bursty. Sometimes there's high peak usage, and sometimes there's not that much request. If you always plan for the peak usage, you probably are overspending your GPUs on these agentic workflows. So our observation is that by leveraging GPU fractionalization, such that you can divide the GPU among this agent and then consolidate them into fewer GPUs, you can free up your GPUs for other competing workloads to run. Next, I'm going to walk you through the demo setup. So there's a lot going on, so I kind of want to hit a few points before I hand it to Zhiming for a live demo. So if you're an experienced AI workloads practitioner, I hope our demo, you can walk away knowing that you have Kueue, you have fractionalization that you can play with to get more bang for the bucks for your GPU capacity. If you're new to agentic workflows, I hope that you walk away knowing that, oh, you can try this recipe on the GPU, on a cloud that have AMD GPU to know that it will work. So I'm going to break the demo setup into 3 parts. First, let's cover the top part. What are the hardware we're using in this demo? So we used 3 AMD MI325 GPUs. MI325 is AMD's high-end data center GPU. The current flagship offering is actually MI355. Both MI325 and MI355, MI325 come with high GPU memory bandwidth, also with almost 300 gigabytes of GPU memory capacity. What this means is that the GPU can fit massive model on it. This reduces the cross-GPU communication and can keep the latency low. The second feature is the multi-user GPU virtualization through single root I/O virtualization. What this translates is that it can virtualize the single physical GPU into multiple virtual GPU and assign to each tenant. The tenant could be each virtual machine, or it can be a pod that can see a dedicated virtual GPU. And what this gives you is that it can have strong isolation between the tenant, so make it more effective to support multi-tenant with high performance, as this feature is implemented in hardware. The second part of the demo is going to have 2 competing workloads. The first one is the agentic workflow. We use a prompt chaining like Yuchen introduced that have a user input request that go through 3 agents and then have the output. And then we have a background task, which is GPU compute intensive. Finally, what's installed on the Kubernetes here? The Kubernetes we have a queue setup, and we have the AMD GPU and memory fractionalization software enabled. Now I'm going to walk through the workloads and the Kubernetes setup. First, let's make this a more real life, what it could look like. So you have an input of an image. The image could be a frame capture from the security camera, or it could be a user uploaded image. What the first agent is going to do is it's going to generate an image caption. The model we choose in this demo is the blip image caption base. And its compute usage is compute intensive and low memory. The output of the first agent is then going to feed into the second agent, which is going to reason and analyze the caption. The model that we're going to show is a Quantum 7B model. It's a high compute and medium memory in this use case. Finally, the output of this analysis is going to the third agent, which is going to plan action. Imagine in the security scenario, it might be we want to alert the security, we want to log the incident, etc. In the third agent, we choose the same model as the second agent, Quantum 7B model. But as Yuchen mentioned earlier, sometimes even with the same model, because the third agent needs a long context, the same model kind of have a different resource requirements. It becomes memory bandwidth bound because it needs long context. So this agentic workflow kind of setup give you an idea about really each model will have different kind of compute and memory requirements. Now let's look at the demo setup. So on the left-hand side, you will see a resource pool of 3 GPUs. On the right-hand side, you'll see two queues. The top yellow one is a demo queue, kind of the high priority because the agentic workflows have the user waiting for the reply. And the bottom is a background queue. So also the top demo queue, we give it a guaranteed quota of 3 GPUs because we really need to make sure all 3 agents run at the same time to be able to collaborate and finish this user request. In the demo, you're going to see kind of a before and an after. Before is a dedicated GPU scenario where we assign each agent to have 1 GPU. Since the agents are higher priority, so queue will omit them and then put the background task into a pending state. But in this demo, we're going to show that there's actually not that many user requests coming in. So dedicating 1 full GPU is a bit wasteful. Let's see what we can do with fractional GPU. So we divided the memory such that agent 1 uses a bit less than agent 2 and 3, but they all can fit into 1 GPU. At this time, queue happily omit the 2 background tasks to run on GPU 2 and 3. So what we will show is that all 5 workloads run on the same 3 GPUs, but the latency requirement is still met, but we're able to fit in more workloads on the same capacity. Now I'm going to hand the presentation to Zhiming to show us a demo.
All right. Thanks, Jodie. Right. Sorry, I have one of my colleagues to hold the mic for me. Hello, everyone. So, really excited to be here to share what we have done, with AMD team. Let me end the slideshow here. So, it's really exciting to be here to share what Exostellar has been doing with AMD. And today I'm going to show a live demo, because why not? Live demo never goes wrong, right? So, like this mic.
But AMD.
Just in case, I do have a video recording, so if anything goes wrong, I'm going to just blame the Wi-Fi of the conference. You see this? I'm going to blame the Wi-Fi, I'm going to switch the video. But hopefully my terminal is still working. Okay? So, on the screen right now, you're going to see like 4 different windows. On the bottom right, you can see we have, the current status of the cluster queue. If you attended the previous talk, you probably will know that cluster queue is one of the most important concepts introduced by queue. Each cluster queue is basically, it carries the resources quota, it carries the priority, it carries some like scheduling policies. In this case, we're going to use, 2 queues here. There's one queue called background queue here, and another queue called demo queue. The background queue doesn't have any quota, it's basically running on the borrow only resource. The demo queue is the one that has the quota. On the top right, this is the, one of the machine we carve out for the demo. And by the way, if you notice, probably, on the screen on the bottom right, it is actually a cluster in production. So what we have done is we just carve out a node from the AMD cluster, and then we basically assign a 3 GPU quota for the demo. while the other workloads can run in the original queue. So it's like isolated, handled by the queue. So this just shows how flexible it is to use queue to basically create different quota, different projects, for different initiatives. So the top right shows the AMD SMI command output, which is actually available on the latest and greatest AMD ROC M7 software suite. So it shows the GPU, like Jodie mentioned, is MI325. Right now, there is no process running. It's basically an idle machine. On the top left, this shows the current status of the demo namespace with all the pods listed here. Right now, we only have 2 pods running and no GPU workloads running yet. So without any further delay, I'm going to run the demo script. As a starting point, I'm going to show you the background queues. The background queue is just like I said, it's a queue with 0 quota on the resource flavor that we define. And by the way, resource flavor is pointing to the node that we just covered. You can see all the quotas are 0. And by the way, in this queue concept, a quota is different from the Kubernetes namespace concept, right? Namespace quota is a cap, but for this one, it's actually a guaranteed resource. When you see a 0 quota, it means there's no guaranteed resource. It's going to run only on the borrowed resource. And there's one extended resource here, is called SDG and /gigabyte. This is the fractional GPU resource that we define in the cluster. And each unit here is basically corresponding to 1 gigabyte of the AMD GPU memory. And this is how we implement the fractional GPU, and this is how we actually integrate the fractional GPU with the queue here. So as you can see, all of the quota here are 0, and then the borrow limit is also unlimited because we didn't set any borrow limit. So if I go to the next one, the demo queue is different. Demo queue is basically pointing to the same resource flavor, but we have all the quota numbers specified here. So particularly for the fractional GPU resource, it's 765, which is actually corresponding to 3 full GPU memory. So this is how we allocate actually 3 GPUs for this demo queue. And after this, let me show you, as a starting point, we're going to submit 2 background workloads. The background workload is very simple. It's a PyTorch, training workload. It's going to allocate pretty much full GPU memory. It's going to do some background job over there. Once this job starts running, you're going to see a couple processes running on the AMD SMI outputs. And you can see now we have 2 processes, PyTorch processes running. Each one is actually using 230 gigabyte GPU memory. This column particularly shows the GPU number, and you can see these 2 processes are now running on 2 different GPUs. So this is the background job. But while this background job is running, and the reason why this background job can be running is because the quota owner, which is the demo queue, has no workload yet. So if you look at the bottom right, the cluster queue, the background queue has now 2 workloads admitted to the queue, and then the demo queue doesn't have any workload yet. But once we submit a full GPU workload, it's going to start the 3 agents that we just talked about. Each agent is going to request 1 GPU, and as you can see already, the background jobs are terminated because they are preempted. The jobs are submitted to the demo queue, and we are now admitting 3 jobs to the demo queue. And then the background queue now has 2 jobs pending. And this just shows in action how queue actually handle the quota and the preemption. And you can see now all the background jobs pods are pending, and our agents are running. And while we're waiting for the agent to be ready, let me show you the YAML spec of the agents. I want to particularly call out, there are a couple labels here. The queue name here, you can see, is actually from it's actually pointing to a cluster, a webhook that we define for the cluster, and we just want to make it easy for the end user to use the queue. So we actually have our own webhook and our CRD to wrap the queue interface. In this case, you can see the queue is pointing to the cluster queue, and with this, our system is going to automatically find out which local queue to point to, and it's going to configure the local queue. And there are 3 labels here. It's actually all about fractional GPU, and they are all labeling. And once you label this, it's going to trigger the webhook, and we're going to replace this with the real resource that we just talked about. But in this case, you can see the agent is requesting 255 gigabyte GPU memory, and then every agent is going to be like this. So this is agent 1, and there are 2 other agents in the YAML spec, but they are all similar. So while this, let me see if the, okay, so now all 3 agents are up and running. So let me switch to the simple demo UI. I'm going to show you how this 3 agent works. So I'm going to send the URL of an image to the first agent. It's going to return and tell us, like, the first agent is going to say, okay, this picture is about a group of ducks walking down a road. And then the reasoning agent, this output is going to be fed into the second agent, and the second agent is going to, have a reasoning about this picture. And you can see it has, it says the behavior can be attributed to several possibilities. And then the reasoning is going to be passed to the third agent, and the third agent is, you can see, is print out a plan for this. So this is just a simple, very simple multi-agent workload. For the demo, I'm going to just start a workload generator with the locust and quickly show you a little bit of performance. And we intentionally tune this workload so that it's kind of like lightweight. So while this thing is running, let me get back to the terminal. So from AMD SMI output, you can see if we do receive a request, we do have some like GPU usage, but it's pretty lightweight. So and the agents are pretty small. So it's definitely an overkill if you allocate such a big GPU for each agent. So then that's why we need a fractional GPU. So we would like to show you how a fractional GPU solution is going to make this whole thing better. So as you can see, the locus print out like a little bit about the latency and the throughput. We are about like 1.7, 1.5 latency, 1 second, and this is the end-to-end latency across all 3 agents, right? Every request is going through the whole pipeline. So let me stop this. I'm going to switch back. I'm going to delete the full GPU workload. So all 3 agents here will be deleted. And once we delete it, Kueue is going to see that the quota owner just released the quota. So then the background job will come back to run again. So because once the quota owner released the resource, then the background job is going to kick in. And with that, let me submit a fractional GPU workload. Like I said, the fractional GPU is going to ask for a much smaller memory size, so then it will not actually cause any termination because we just need 1 GPU to host all 3 agents together. So as you can see now, we have all 3 agents running, and the background jobs are still running. There's no termination yet. While we're waiting for that, let me show you the fractional GPU's YAML spec. We don't need to request a full GPU, so we just change the label here to make it a much smaller size. Every agent, like first agent is asking for 50 gigabyte GPU memory. The second and the third one is they are asking for 100 gigabyte GPU memory each. In total, they are good enough to fit into 1 GPU. So then let me switch it back. So we're still waiting, but while waiting, let me show you one important thing. So the reason why we need a very good like a GPU virtualization, especially fractional GPU solution, is because the default behavior for VLM, and by the way, the agents are using VLM. The default behavior is that they're going to detect the GPU size at the beginning, and then by default, they're going to allocate 90% of the GPU memory for the KV cache. And if you don't provide a good enough GPU virtualization solution, you just slow them onto a time slicing system, all of them are going to detect the full GPU memory, and they are going to all try to allocate 90% of GPU memory. It's going to crash. But with the fractional GPU solution that we show here, the VLM is going to just detect 100 gigabyte GPU memory that we just allocate for them. And then it won't allocate too much. So for example, in this case, you can see VLM says, I'm going to allocate like 69 gigabyte. And that's because it only detects 100 gigabyte total GPU memory. So that's how we make sure that it's completely transparent to the workload. Okay, so now I think the agents should be running. So let me switch back to this terminal. Let's send the same request, and you can see the 3 agents are working pretty much exactly the same as before, even though they are running on a single GPU. I'm going to go back to the locust, restart the workload generator. They're going to send the request, and we're going to get very similar performance. Initially, it might a little bit high, but it will come back. But the point here is that all the agents now are running on the same GPU without affecting the other workloads that are running in the background. So we effectively improve the overall cluster usage. Okay, with that, let me switch back to our slides. So what we just show you is, a solution to integrate the fractional GPU with the queue, and then we can allocate quota. We can, allow different teams, different projects to share the cluster in a much more efficient way. And with that, we kind of, dramatically improve the overall efficiency of the cluster. And we also show you how queue actually handle the preemption with the background and the foreground job. And if you have any question, like, we have a booth at 5:42, and feel free to come to our booth, and we'll be happy to talk more. Thank you very much, and we'll be happy to handle questions. Yep.
Can you sort of articulate the differences between what you showed here and what we do with CPUs? I mean, so that it's very, very clear, what is the exact difference of what you did with what somebody would do without GPUs? I mean, what's the secret sauce here?
Well, I think queue itself is general. So what we show you is that we actually define an extended resource in Kubernetes, which is a fractional GPU. Right? Each unit is actually a 1 GB of the fractional GPU. But for queue, you can actually, and with that framework, you can define any resource in the cluster, and queue will be able to manage it, right? So as long as it's a resource that is under management in Kubernetes, then you can actually define it in the queue, in the cluster queue, and then queue will be able to manage it. So in terms of the queue, I think it's a general framework. Yeah. So yeah, I don't think there is any fundamental difference here. But what I didn't show you is actually, if the DRA is actually enabled in this cluster. By the way, this cluster doesn't have DRA, but if DRA is enabled in the cluster, then the resource will be shown in a different way. But again, it's basically tapped into the Kubernetes framework. For queue itself, it actually doesn't care.
Okay, so just to summarize, so, instead of a CPU, you just allocated a fractional GPU. That's the only change you made, right?
Yeah, that's a resource that is visible in Kubernetes.
Okay,
yeah.
All right, thank you.
Hi, I had a couple of questions. First one, which cloud is this available in?
This is the internal AMD cluster.
Okay. This runs on voucher.
Oh, okay.
Yeah.
And then the second question is, for the GPUs themselves, how finely can you partition them, practically speaking?
1 gigabyte of memory, and then compute is 1% compute.
Okay, thank you.
Hi. First question. Does Queue enforce what's the amount of VRAM actually a workload can allocate, or it's something that just acts as a scheduling level?
So you mean enforce the cap?
Yeah.
Yeah. So
the amount of the workload, the VRAM that the agent can actually allocate.
that's not enforced by queue. Although queue will make sure that, if you set a quota or you set a borrowing limit, queue will make sure that you don't go beyond the borrowing limit. But in terms of the capping of the fractional GPU is handled by a fractional GPU solution that we put into the cluster.
Okay, so it can happen that a workload allocate more than the quota has defined by queue?
It's not possible.
Ah, okay.
Yeah, because it's going to be capped by the fractional GPU solution.
Okay, thank you.
Our time is up. Let's take the questions offline. Our time is up, so just come to the front. Yeah, thank you everyone for coming. Really appreciate it.